Okay, recording is started. All right, good morning, everybody. Welcome back to Math 115. Let's see. Today, what are we going to do? We're going to talk a little bit more about quadratics, because I didn't quite finish last lecture. And then we're going to move on and talk a little bit more about kind of general polynomials. Okay, so let me share and get the notes up. Okay, I'm going to try hard to make today completely mistake-free. I made a mistake right at the end of the last lecture that I need to correct, okay? So that's the first thing I want to talk about is at the very end of last lecture, we were talking about the domain and range of quadratic functions, okay? And we established that the domain is going to be all real numbers, okay? And I was rushing towards the end, and I initially, where I had this k here, I wrote an h, okay? Where I was talking about the range of a quadratic function, okay, I said that if a is a positive number, okay, so we have a quadratic which is opening up, I said that the range of that function was going to be from h to infinity. But the y value here of this vertex is actually k, not h. Okay, so I mixed up my letters there. So that should have been a k. Okay, and we can see that if we remember what we talked about range, we said the range is all of the values which are on the y-axis, such that I can draw a horizontal line through that y value and touch the graph of our function at some point. Okay, and that's exactly going to be all of the points which are above the vertex, right? If I choose any point on this axis, I can just draw a horizontal line and I'm going to hit the graph, okay? But if I choose a point which is beneath k, like say this one here, and I draw a horizontal line, it's never going to intersect the graph of our function, okay? So that won't be in the range. Okay, so the y values, basically, if we were to collect all of these points which are along this parabola, and we wrote down the collection of all of those y values of all of those points, well, we know that the lowest one is going to be at the vertex, and then the highest one, well, there is no highest one. It's just going to go up to infinity. Okay, so that was about the range of a quadratic function. And we had that if a is less than 0, then it's going to open down, and rather than having a minimum y value, we're actually going to have a maximum y value. Okay, and this guy is going to go down and down forever. And if we are to collect all of these points which are along this parabola and write down the collection of all possible y values of all of those points, it's a bad looking k, let me redraw that. Then it would be the collection negative infinity comma k. All right, so sorry about that mistake. I'm going to do my very best to keep everything totally kosher today. Okay. Let's see. I'm going to try to speed up just a little bit so that I can get through all of today's material. This section that they gave us has a lot of stuff in it. So if I wind up going too fast, just let me know. I'll slow down and we'll wind up maybe taking an extra day on this stuff. But hopefully we can get through everything. Okay, so we can do this example here. We have this function f of x equals x squared minus 2x plus 1, and we want to find its domain and range. So the first step would be get it into vertex form. Or they call that, quote, standard form. Or vertex form. Okay. And recall, the way that we want to do that is by first expressing this where we put some parentheses around our x terms, x squared minus 2x. I'm going to leave a little extra space because my goal here is to then complete the square. Okay. In fact, I don't even need to complete the square because this is already a perfect square. Okay, this is already a perfect square. This would factor as x minus 1 squared. We can just factor it directly. Okay, but if we were to complete the square, what we would do is we'd write it like this, and then we would take this number here, -2, we would divide it by 2, and then square it. So if I take 2 divided by 2 and square it, I would get +1. And then I would need to undo whatever I did, so I would subtract 1 out back. And we're just going to get, if we do that, we would just get back exactly what we started with, x squared minus 2x plus 1. And what that tells us is that our function here was already a perfect square. And so we can just go ahead and factor it. Okay, so if this is my vertex form, x minus 1 quantity squared, I can kind of think of there being like a +0 back here, okay? +0. So then this here, this 0 is going to be my k value. And this is telling me that h, remember, this is the expression x minus h. Okay, so if it's x minus 1, then h is 1. Okay, so this is we're going to have a vertex at the point 1, 0. And the direction of opening is up. Therefore, the domain, I don't even need to think about the domain. It's just going to be all real numbers. I'm going to use this fancy R sign again to mean all real numbers. And what's the range of this going to be? What should the range of this parabola be, this function here? A collection of all y values. Yeah, I think Savannah's got it. 0, infinity, right? We just take our k value, which remember was 0, and since it goes up from 0, we just start with 0 on the left with a bracket, and then we go up to infinity. Okay, you could draw the graph if that helps you visualize what's going on here. We would go to 1, 0, that's this point right here, and we would draw a parabola going up like this. So if we want to collect all the possible y values such that they intersect the graph with a horizontal line, it would be all of the y values which are above 0. But we would not include a y value which is below 0, because that's not going to intersect the graph of the function anywhere. Okay, some other people coming in with the same answer. Very good. Okay, so that's how we do domain and range of quadratics. Really, all we have to do is worry about the range. And the range is just going to be all the y values which are higher than the y value of the vertex if we're opening up, or lower than the y value of the vertex if we're opening down. Okay, so let's talk about quadratic inequalities briefly. Okay, so suppose we have some quadratic function f of x, and we get this, we want to find the x values such that our quadratic function, when we plug x into the quadratic, we get something which is larger than or equal to 0. Okay, so we have a quadratic function, and we want to check where is it larger than or equal to 0. Okay, and the best way to do these quadratic inequalities is to use the graph of the function. Okay, that's how you're going to be able to visualize this the best. Okay, so if I have something like this graph of this function here on the left, part A, and I look at the graph, it's going to tell me exactly where this function is greater than or equal to 0. I just need to check where is the y value of the graph larger than or equal to 0. And that's going to be in all of this region right here up until I hit this point, and including it since I have a less than or greater than or equal to sign. And then all of this region here. Okay, and then we're not going to include any of this region, okay, because that's beneath the x-axis, and that would mean that f of x is less than 0. Okay, so this is kind of the region that I'm interested in, is this green region. And what I'm supposed to do is I'm supposed to find the x values that cause me to be in the green region. Okay, and remember our x values lie along the x-axis. So why don't I use green here? Find the values x such that this is true. Well, it's going to be all these points along the x-axis here such that when we draw a line that goes to the graph of the function, the line goes up, right? So all of these here as well that go up. Okay, so what this is telling me is as long as I know where the zeros of the function are, okay, as long as I know where it crosses through, I'm going to have no problem telling you what x values this function is larger than or equal to 0 for. It's just going to be all the x values which are to the right of x2 or to the left of x1. So in this example, my answer would be x in negative infinity comma x1 union, and I should actually use a bracket here. I should use a bracket since I have greater than or equal to. Okay, and f of x1 is actually equal to 0. Okay, that's what it means for x1 to be a 0. So I'll use another bracket on x2, and then that'll go to infinity. But I'm not going to include any of the points which go in between x1 and x2, since that would produce something like this red line here, right? And the red line goes down to the graph, okay? If I take this x value, call it x3, we have f of x3 is less than 0. And that's incompatible with what we're trying to establish, which is the x values for which f of x is larger than or equal to 0. Okay, so that's a situation where we've got two zeros, two real zeros. On the right here, we can see the graph of a parabola which has no zeros at all, or no real zeros. And if we want to check where this graph is larger than or equal to 0, well, it's kind of the whole thing, right? So the whole thing here is actually going to be larger than or equal to 0. So if we want to describe the x values, which produce a y value larger than or equal to 0, well, it's going to be all of the x values, right? And we know that the domain of the function is all real numbers. So here we would say x is a real number. Or we might write x is in big R with an extra line. Okay? So all of those are permissible x values. Okay, let's see a couple more examples. We'll try now one of these ones. Let's try this part A on our own, okay? So we want to find values x such that f of x is less than or equal to 0. So let's see, how would we describe the set of x values such that this graph here of A is less than 0? What do we think? Yeah, right. Kind of a trick question, Savannah. No solution is exactly right. We could write that with one of these, right? Here's why. I want to check where is f of x less than 0. That means that the graph of my function should lie beneath the x-axis, okay? It should be in this region. But none of the graph is in that region. In other words, all of it's in the bad region, where it's not true. So there's no x values such that f of x is less than 0. In fact, we're going to get the same result for part B, right? Because all of it lies above or possibly on the x-axis. Okay, but this point h comma k here, this vertex, is still not going to satisfy f of x is less than 0 because k is actually equal to 0, and 0 is not less than 0. So it's still going to be thrown out. So this one, again, our solution is going to be no solutions, or our answer is going to be no solutions. Okay. But we can try this last one here where we have f of x less than 0. We're going to have a region where it actually does pass beneath. Okay, so this stuff is going to be bad. And the region we're interested in is the x values, which produce y values beneath the x-axis. And strictly beneath. So I'm going to use parentheses around my zeros here, x1 and x2, because I know that if I were to actually plug them in, I would get 0, and I'm looking for the places where we're strictly less than 0. So these parentheses come from the fact that we have less than signs. Okay, but not less than or equal to. All right, so let's see how we do this in practice. If we have just the algebraic expression for a quadratic, and we want to know where is it larger than or equal to 0. Okay, well, I think the easiest thing is just graph the roots. Okay, so to find the roots, I'm going to find the factors. Okay, so I'm going to first rewrite this as negative x squared minus 4x plus 3, just so it's easier to factor. I want to know, where is this larger than or equal to 0? Okay, so I'm going to factor this now. We'll get x minus 3 times x minus 1 as well, right, is larger than or equal to 0. Okay, so this has zeros at x equals 3 and x equals 1. So let me graph the zeros first. They're going to happen at x equals 1 and x equals 3. Okay. And now if I want to graph this thing, I should note that because I have a negative sign out front of my leading term, this is going to be a parabola which opens down. Okay. In this case, we have a equals negative 1 is less than 0. That tells us that this is going to open down. Okay, so we have these two zeros, and we know that this opens down. So it looks something like this. It doesn't really matter where the vertex is, because we know that in between these two zeros, we're going to be larger than or equal to 0. And to either side of them, we're going to be less than 0. And we don't really care how high we are, so we're not even going to worry about putting this into vertex form. We're just going to graph the roots. And if we want to fully complete this answer, we should say that x lies in the interval (1, 3). And I'm going to use brackets because, again, I have a less than or equal to sign up here. So that's why I use the bracket. Okay, so that's how we would solve that quadratic inequality. All right, so that's all that I have to say about quadratics. Before we move on and talk about general polynomials, let me pause and see if there are any outstanding questions about quadratic functions. Okay, seems like not. If you think of anything, feel free to put it in the chat or ask after class or something. Okay, so let's move on and talk about polynomials. Okay, so a polynomial function has this form in this blue box here. Okay, so let me explain what the heck all of that jazz is, because it looks kind of monstrous. Okay, each of these ANs here, these ANs are just numbers, okay? AN and AN minus 1 and A1 and A0 are just numbers, okay? And these x's here are just different powers of x. Okay, so we have x to the power n, and then we have some term an minus 1 times x to the power 1 less than that, and then all the way down until we hit x to the power 1, and then we have kind of a floating x to the power 0 on that last term that we usually don't write because x to the power 0 is just 1 for any x. Okay, so that's what's going on here. So a polynomial is just something like, for example, you could have like, I don't know, 3x cubed plus 2x squared minus x minus 3. Okay? In this case, n would correspond to 3, and an would just be the number 3, and an minus 1 would just be the number 2, and then a1 would just be the number 1, and then a0 would be the number -3. Okay, so that's how this notation is just working. So don't be intimidated by the fact that we have all these different numbers and letters like all crazy all over the place. Okay, and we require that n is going to be a positive integer, okay? So we don't do things like 3x to the 3 halves, okay? This is not a polynomial. Okay, the reason being that 3 halves is not a positive integer. Okay, it's positive, but it's a rational number. Remember, integers are whole numbers. Okay, so we require all of the powers on a polynomial to be whole numbers, like 1, 3, 5, 7, these sorts of numbers. Okay, so n should be a positive integer, and we require that an not be 0. Okay, again, we always require this top term to be non-zero. And that's really just for the sake of establishing what is the degree. But let's first talk about what the leading term is. The leading term of a polynomial is just going to be an times x to the n. Okay, that's the leading term. So that's this very first piece in its entirety, everything that goes before the first plus sign, basically. Okay, so for example, if we have 3x cubed plus 17, the leading term is going to be 3x cubed. Okay, so that's a polynomial, and that's its leading term. And the leading coefficient, okay, is just going to be the number, which is being multiplied times x to the n. It's just going to be an. Okay? Leading coefficient is an. Okay, and the degree here of my polynomial, since I required that an is not equal to 0, the degree is just going to be the highest integer for which an is not equal to 0. So in our case, this is going to be n. Okay. And finally, the constant term and the constant coefficient, those are kind of interchangeable terms to mean the same thing. We're talking about a naught. If we're talking about the constant term or the constant coefficient, we're talking about a naught. Okay, so this is sort of the anatomy of a polynomial. In the blue box, we have the general form, and then here are some words we use to describe different parts of it. Okay. So let's talk about a couple properties really quickly. First of all, graphs of polynomials are going to be continuous. Okay, so continuous means no jumps and no holes in the graph. So here's a continuous function. Sometimes we write just CTS to mean continuous. And here's a function which is not continuous. Okay. Sometimes what we say is we can draw it without picking up our pencil or our writing utensil, I guess. I'm using an Apple Pencil. Okay, so if we can draw it without picking up our writing utensil, then it's going to be continuous. Otherwise, it's not continuous. And there's two places where this second graph is not continuous. It's not continuous at this x value, since we have a jump, and it's not continuous at this x value, since we have a hole. Okay, so polynomials have this nice property that their graphs are nice and smooth and continuous. So let me talk really quickly about what smooth means. Smooth means no corners or kinks. Okay, so again, continuous, nice and smooth and curvy. So this is smooth. And not smooth would be something like this. Absolute value of something, maybe. Okay, so here's one that's not smooth. And it's not smooth at this point here, where we have a corner. Okay, but it is continuous. This graph on the right would still be continuous since I can draw it without picking up my pencil. But it would be not very smooth, right? I mean, if you were to like run your hand over this thing, this would be like a pointy part. We don't like pointy things. Okay, so that's about the graph of polynomials. They're going to be continuous and smooth. And the domain of a polynomial is always all real numbers. Okay, so that's one nice thing about polynomials, is as long as you can establish that the function you're working with is a polynomial, you can just write down that its domain is automatically all real numbers. Okay, so that is about the graphs of polynomials and their domain. Now let's talk about end behavior. Okay, so I'm going to introduce some notation here. And end behavior, what we're talking about here is if we have a polynomial, let me draw your attention back up to this graph here of this smooth one. When we talk about end behavior, we talk about as we go really far to the right and really far to the left, what is happening to our function? Is it going up, 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 and up forever? Is it going down, down, down forever? And are the two sides having the same type of end behavior or different end behavior? Okay, so this is some notation that we sometimes use to talk about end behavior of polynomials. Okay, so I've color-coded this here, but let me just go through really quickly. If we have f of x going to positive infinity as x goes to positive infinity, what we mean is that as x increases, the value of f of x increases without bound. And I should write to plus or minus infinity, whichever one is applicable. Okay, so as x goes to infinity, the value of f of x is going to infinity. Okay, that's what we're saying here. And sometimes we say as f of x goes to minus infinity as x goes to positive infinity, or f of x goes to positive infinity as x goes to minus infinity, or f of x goes to minus infinity as x goes to minus infinity. Okay, the other notation that you might see for this is lim as x goes to infinity of f of x equals infinity, that means the same thing. Basically, this means f of x goes to infinity as x goes to infinity. And why they introduced this notation and not the other one is really beyond me, but there it is. I'll close it off. You don't actually need to know this, but if you're going to do future math, you'll probably see that at some point. Okay, so that's notation. So let me draw really quickly what this one means. So here we have f of x going to minus infinity as x goes to positive infinity. And what end behavior tells us about is really just what's happening to the graph really, really far to the right. Okay, so the only thing that I can really establish about this polynomial is that way to the right, we're going down, down, down forever. Okay. If I also added this statement, f of x goes to infinity as x goes to negative infinity, then I would also be able to establish that way, way, way to the left, we're going up, up, up forever. Okay, but crucially, I'm not really saying anything about what's going on in the middle. Okay, this is just about, after a very long time, where is the height of our function going? Okay. And the reason we can kind of say this, okay, the reason we can kind of say this is by looking at this first term here, right? If we have f of x equals like 3x cubed minus 10x squared plus 2, okay, if we consider x getting very big, we're going to notice that 3x cubed will outweigh negative 10x squared plus 2. When x is 0, then we're not really sure. But if x is something like 100, then 3x cubed will be 3 times 100 cubed. That's definitely going to be way, way bigger than, let me just say that it outweighs negative 10 times 100 squared plus 2. The reason being that 100 cubed is a much, much bigger number than 100 squared. In fact, it's 100 times bigger than 100 squared. Okay. So this is why we're able to say these things about polynomials, is by looking at this leading term. Okay. So that's leading into this leading term test. Okay, so I've got this nice table here to kind of describe what's going on with the leading term test. Okay. So first of all, we consider f of x to be a polynomial of degree n. In other words, f of x equals a n x to the n plus dot 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 plus a1x plus a0. Okay, and the leading term here is a n x to the n. Okay, so we break this first into two cases. We break it into a case when n is even and when n is odd. So let's talk first about when n is even. Okay, so if we have something like, I don't know, x to the fourth is the leading term. Something like that would be an even number or even degree. Okay, and something on the right side would be something like x to the fifth. That would be an odd degree. Okay, so for an even-powered polynomial, or a polynomial of even degree, if the leading coefficient is positive, then we're going to have f of x going to infinity as x goes to plus or minus infinity. So we have same end term behavior. Okay, same end term behavior, and they're both going to positive infinity if an is positive. Okay, and if an's negative, then both ends go to negative infinity. Okay, this should make sense because if we think about something like, okay, this one, here we have an equals 1, which is larger than 0, and n equals 2 is even. We know what the end behavior of this parabola looks like. We have both of those terms going up, up, up forever to infinity. Okay, but if we have something like negative 3x to the power 4 here, well, we have an even degree polynomial, but an is less than 0, so we know that both ends are going down forever. Okay. Now, if n is odd, okay, we're going to observe opposite end term behavior, okay? And that makes sense because it should kind of fit with what we know the graph of x cubed looks like, right? It comes up from the negative infinity and goes all the way up to positive infinity on the right side, okay? And we know that if we were to flip it, then it would look something more like this graph of negative x to the power 7th. And we would take all of those things which were negative on the left side and we'd make them positive, and we'd take all the things that were positive on the right side and make them negative, and we're going to observe this kind of end behavior. Okay, so this table is just kind of like your comprehensive key, so that if you start with a polynomial, you can kind of go through this table and get where you're trying to get. Okay, so first you'd establish whether or not n is even or odd, then you'd establish whether or not an is positive or negative, and then you're just going to get the result which, you know, goes down there. So for example, if I had like 5x cubed, I would know that that fits into n is odd, and then I would know that 5 is larger than 0, so then I would know that the result is going to be that f of x goes to positive infinity as x goes to positive infinity, and f of x goes to negative infinity as x goes to negative infinity. Okay, are there any questions about this table and how to use it, or about end term behavior? Does this stuff make sense, or is it confusing? Okay, a little bit confusing. Maybe we should do a practice. Okay, so let's do a practice then to make this a little bit more clear. A question might ask something like, establish the end term behavior of f of x equals negative 3x to the 7th plus 21x squared minus 13x plus pi. Okay, so here we have a polynomial, and we want to know what is the end term behavior of this function. Okay, so what we mean by establish the end term behavior is we want to do some work and then eventually write two statements. The first one should be something like f of x goes to blank as x goes to infinity, and f of x goes to blank as x goes to negative infinity. Okay? And what the leading term test says is that the only thing that we need to worry about is the term with the largest power of x. Okay? So leading term test. Just check what happens to the leading term when x is really big or really big and negative. Okay. So x very large is going to give us negative 3 x to the 7th equals negative 3 times a very large number. Okay. And as this number gets bigger and bigger and bigger and bigger and bigger and bigger, the entire thing is going to get smaller and smaller and smaller in a negative way, right? Or bigger in a negative way, I suppose you could say. Just a matter of perspective. It's going to become a really extremely negative number, okay? Because we're going to take a really big number and we're going to multiply it times something negative, okay? So this is going to negative infinity, okay? So now I can fill in this part of my response, which I'm trying to kind of get to. I want to just write, okay, f of x is going to negative infinity as x goes to infinity. Okay, now I can check the other one. Check what if x is very large and negative. Then negative 3 x to the 7th will be equal to negative 3 times a very large negative number. And if I take negative 3 and multiply that times a very large negative number, I'm going to get a very large number, which is positive. Okay? So this means I'm going to positive infinity. Okay, so as x becomes very large and negative, in other words, as x goes to negative infinity, we see that f of x is becoming very large positive number, in other words, going to positive infinity. So that's the spirit of the leading term test. Okay, and this is just to establish the end term behavior. We're only worried about what's happening to this function when x is going to positive infinity or x is going to negative infinity. All right, and what the table says is that rather than doing all this work and plugging in like really big numbers and seeing what we get, we can just go to the table and we can see here that the leading term, we've got what? Negative 3 is an, so we know that an is less than 0. And we know that n is 7. In other words, n is an odd number. Okay, so we have n is odd and an less than 0. So I can just go to the table, I find n is odd, I find an less than 0, and I know that this is going to be my end term behavior. Okay. I'm just going to automatically get that f of x goes to negative infinity as x goes to positive infinity, and f of x goes to infinity as x goes to negative infinity. And that's exactly what we established below using our kind of more careful reasoning. Okay, does that make a bit more sense now, Savannah? Okay, cool. All right. So yeah, just to remind you guys that the leading term test, this statement in blue here is kind of important. The leading term test is only going to tell us about the end behavior, okay? It's going to tell us what's going on way on the ends, okay? But it's not going to tell us what's happening in the middle, okay? That was the reason that I drew, where did I draw it? I drew this graph here where I drew kind of this stuff on the sides, okay, because I know what's going on the sides, but I don't really know what's going on in the middle, okay? So be careful not to get too carried away and say that just because the end term behavior looks like this, well, the middle could look all sorts of different ways, you know? It might look really crazy. Okay, we're just saying what's happening on the ends. All right, so let's talk about zeros of functions. Okay, so this is just terminology. We say that C, a number C, is A0 of f of x if this statement holds. Okay, so if f of C is equal to 0. Okay, so that means we have an x-intercept at x equals C. Okay, this is just the definition of how we say this. So on this graph of this polynomial here, we can see the zeros are written down in red. Okay, they're pointed out in red. They're going to be the points where we cross the x-axis or touch the x-axis. Okay, sometimes we have zeros, in fact, which might look more like, might come down and just barely touch and then go up. Okay, that would be a more complete picture. But a zero is just a place, an x value at which our function touches the x-axis, either by passing through or by bouncing off. Okay? So here's a fact. If f of x is a polynomial and f of c is equal to 0, then x minus c is a factor of f of x. Okay, we've seen this all the time when we talk about factoring polynomials, right? If we take x squared minus 3x plus 2 is equal to 0, we would factor the left-hand side. We'd get x minus 2 times x minus 1 is equal to 0, implies x equals 2 and x equals 1 are zeros. We could check that. 2 squared minus 3 times 2 would be 6. Plus 2, yep, that's equal to 0. So 2 is a 0. And we can check if 1 is a 0 by doing 1 squared minus 3 plus 2 would also be equal to 0. Okay, so those are the zeros. And what this fact is just saying is that if x equals 1 is a 0, then x minus 1 will be a factor of our expression. Not really saying anything fancy here, other than we're sort of describing what is the difference between a factor, okay, and a 0. Okay, a factor looks like x minus c, and a 0, we just say c. We just say c is a 0. That's how we talk about zeros. And we would say x minus c is a factor. So that's the terminology. Okay, so now we're going to talk about something called the intermediate value theorem. You might have seen this before in another math class. If you carry on to calculus, you will definitely see more of it. Okay, and what I'm going to give you is an intermediate value theorem, which is slightly different from the one in the book. And I really don't like the one that's in the book because it's very limited to a very specific setting, which you will probably not really see in future math classes. So I don't feel like teaching you guys something that you're never going to see again, because that would just be kind of pointless. So we're going to get the more general version. Okay, so let's first talk about what the setup for the intermediate value theorem is. So we have f of x is some continuous function, meaning I can draw it without picking up my pencil. Okay, I have some number a which is less than the number b. Okay, these are x values. And I have that the function height is different at x equals a and x equals b. Okay, so this is my setup. I just have a continuous function, some x value a, which is less than another x value b, and I have the height of the function is different at each of those 2 points. Okay, so if I were to graph this, it might look something like this. Okay, I have my x values a and b here. I have a nice, smooth, continuous function that I can draw without picking up my pencil. And I have that the height of these 2 points on the function is different. Okay. Now let's talk about the conclusion. What does the conclusion say? It says, then, if all of these 3 things are true, for any y value, k, which is between the y values of f of a and f of b, then there will be an x value, c, which is between a and b, such that f of c is equal to k. Okay, this is very mathematical language, but it's saying something sort of simple. Okay, it's saying something simple. What is it saying? Let's start by just checking out, okay, we take some y value k, which is between f of a and f of b. Let's just start by taking that. Okay, so I'll draw it with red since I wrote it in red. We take some y value, which is anywhere in between f of a and f of b. Okay, so let's take maybe this one. That's my k. It's a y value which is between f of a and f of b. Now what this says is that there is an x value, c, which is between a and b. Okay, so we have an x value somewhere in this green region, such that the height of the function evaluated at c is going to be that height k. Okay, and if we just draw a little thing here, we can kind of see the exact point that we're talking about. It's going to be the x value, which lies right here. And if we plug it into the function, we get c comma f of c is equal to c comma k. Okay, so there's an awful lot of letters floating around here. So let me just make this a little bit simpler with an analogy. Okay, if you imagine that you are riding on a roller coaster, what the intermediate value theorem says is if at one point the roller coaster is 10 feet underground, and then later on you are 200 feet in the air, then at some point in between, you were at every height in between negative 10 feet and 200 feet. Okay, that's what this says. It's just that if you start at some small value and you go up, 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 then you have to hit every possible height in between those 2 points. Okay, so if I'm on my roller coaster up here later on, then my roller coaster is at some point in between time A and time B. I am at every single height, which is in between the starting height and the end height. Okay. Are there any questions about the intermediate value theorem and what this is really saying here? Okay, I think that's as concisely as I can put it. It's basically if we start at a certain height and we end at another height, and we have a continuous transition between the two, then there must have been a time in between the start and the end where I was at any given height between the starting height and the end height. Okay, this still works if I'm going down, by the way. If my roller coaster goes down, well, same deal is going to be true. If I start at this height and I end at this height, then I'm going to be able to find a point in between such that I was at any chosen height in between the starting height and the end height. Okay, so let me show you an application of this, okay? Application of this intermediate value theorem. We could use it to answer this question right here. So the question goes, does f of x equals negative 2x cubed plus 4x plus 5 have a real zero between x equals 1 and x equals 2? Okay, so they're not asking us to find the zeros. They're not asking us to factor this. In fact, with the current tools that we've equipped ourselves with this semester, we wouldn't even know how to factor that. You'd have to use something like synthetic division, which we haven't talked about. So we don't actually know how to find the zeros of this thing, but we can use the intermediate value theorem to determine that there is or is not a zero between x equals 1 and x equals 2. So let's check f of 1 and f of 2. Well, f of 1 would be equal to negative 2 plus 4 plus 5 is equal to 7. And f of negative 2 would be equal to, if we plug in negative 2 and then, hang on, did I do that right? Negative 2 times 1 plus 4 plus 5. Yes, I did that one. Okay, then if we do 2, why did I put negative 2? That's why it's messing us up. Okay, so if we do f of 2, because x equals 2, we'd get, what, negative 16 plus 8 plus 5 should be equal to negative 8 plus 5 is negative 3. Okay. So if we were to fill in this information, we know that the graph of the function would look something like this. At 1, the height of the function is 7. And at 2, the height of the function is -3. So what do we think? Given the intermediate value theorem that we just learned, can we conclude that f of x has a real zero between x equals 1 and x equals 2? i.e., is there going to be an x value in this green highlighted region here where the graph of the function passes through the x-axis? What do we think, yes or no? Or totally confused about this stuff, I don't understand. Okay, Savannah says yes. Anyone agree or disagree? Okay, lots of yes, right? And it comes from, nice. I like that animated thumbs up. It comes from the fact that f of x is a polynomial, right? F of x is a polynomial, and we know that polynomials, or graphs of polynomials, are continuous. Okay, so we know that we don't know really what the heck this graph of this function looks like, but we know that we have to draw it without picking up our pencil. So I don't know, maybe it looks really crazy, right? But the point is that if we want to get down to this point here, we've got to cross through that x-axis, okay? And whether we do it by doing that, or whether the graph looks more like this, okay? You know, the graph could look really wonky. We don't actually know what it looks like. But we know that there's a point up here and a point down here, and we know that they're connected by kind of a string, which is going to be continuous between the 2 points. Okay, so we don't actually know how they're connected, but we know that they are connected. So we know that there must be a point somewhere in here where we're going to cross the x-axis. It might look something like that, or it might look something like this. But no matter what, we're going to have to cross the x-axis if we want to get there, right? It's kind of like saying, you know, if I'm on a road, I'm driving a car. Here's me in my car. It's a convertible, obviously. And I'm driving this way. It's like, you know, if I want to get to the gas station, here's a Shell gas station. If I want to get to the gas station, I have to first pass the McDonald's. That's really what this is saying. Okay, that's all the intermediate value theorem is saying. Okay. So that's one way that we could use it to answer a question like that without ever even really having to do the really hard legwork of actually finding out what the zeros of this function are. We can just say, well, we know it's above the x-axis and then it's beneath the x-axis, so it must cross somewhere in between. So the answer is yes. Okay, so that's the intermediate value theorem. Oh, sweet. I'm almost caught up. This is great. All right. So the last 5 minutes, we're going to talk about this final topic. Unless, really quickly, are there any questions about the intermediate value theorem or about how we just used it to solve this or to answer this question? Okay, cool. If you think of anything, just let me know. Okay, so let's talk about how to graph polynomials. So before we talk about actually how to graph them, there's one tool that we need to be aware of, or one kind of definition that we need to be aware of, and that is to do with the multiplicity of zeros, okay? So this green box here is telling us about that. And what does it say? It says that a zero c of f of x, so we have f of c is equal to 0, has multiplicity m if x minus c to the power m is a factor of f of x. Now we know if c is a 0, we know for sure that x minus c is a factor. But it's possible that x minus c squared or x minus c to the power m is a factor. So we know we have at least one power of x minus c as a factor of f of x, but it's possible for us to have multiple, okay? For example, f of x equals x squared minus 2x plus 1 is equal to x minus 1 squared. Okay, in this case, we would say that the 0 c equals 2 has multiplicity 2. Okay, so if we can factor out more than one power of x minus c, then we say that that 0 has multiplicity m, where m is the power of x minus c, which we can factor from f of x. Okay, and if c is a 0 of f of x with odd multiplicity, okay, then we're going to observe passing behavior. In our graph, okay? So for example, if we have just f of x equals x minus c, then it's going to look something like this. Well, actually, this would be negative x minus c. We're going to go through the x-axis, okay? That's the point here, through the x-axis. Okay, and if we have m equals 3, well, the crossing of the x-axis is going to look a lot like the crossing of x to the power 3, right? X cubed. It has kind of this wiggly nature where it comes in and smooths out a little bit, but then eventually smooths back out and goes down. So, or 5, or 7, or things which are higher than 1. When we have 1, we have more of kind of this straight through crossing. Okay, and if c is a 0 with even multiplicity, then we're going to see this kind of bouncing behavior. Okay, so if we have a double root or a quadruple root or a sextuple root, that's kind of fun to say. If we have m equals 2 or 4 or 6, dot, 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 you know, even numbers, then we're going to see this kind of bouncing behavior. Okay, and what we know is that this combined with n-term behavior can mostly tell us what the graph is going to look like. We're going to at least be able to say where is the graph above the x-axis and where is the graph below the x-axis. So I'll do this picture here for us. First of all, we see we've got some multiplicities on some of these. Okay, the multiplicity on x minus 3 is 2. It's a double root. We're going to have bouncing. X plus 5, we're going to have multiplicity 3. We should have passing. X minus 2, we should have passing. And x, we should have passing. So the leading term here, if we were to FOIL all of this out, and it would take us a really long time to do it, would just be 1 times x to the power, well, we would collect all the possible powers. This first one would give us x squared, x cubed, that gives us x to the 5 times x, it's x to the 6 times x to the 7th. So our total powers of x is going to be 7. So we know our ends look something like up on this end and down on this end. And then I'm just going to plot each of these roots here. Positive 3 is here. Negative 5 is here. Positive 2 is here. And then 0, right? And all I'm going to do is I'm just going to kind of fill in the gaps. I know I should have passing behavior at x minus 5, or x plus 5, excuse me. So it's going to come in like this. And at x equals 0, that's my next root. I'm going to again have passing behavior, so I have to turn around in order to pass. At x minus 2, again, I have passing behavior, so I should turn around and pass through. And then at x minus 3, since the multiplicity 2 is even, I'm going to have bouncing. So I'm going to come up and then go down, and then I'm going to touch and then bounce right off. And then connect up like this. Okay, so this is going to tell us mostly what's going on with this graph here, okay? It won't completely warn us if we have imaginary roots, but we're not going to concern ourselves with imaginary roots at this time. Okay, well, I got through everything that I wanted to get through today, so that's fantastic. I'm 1 minute over time again, sorry about that, but we'll end class here, and if anybody has any questions, feel free to stay after. Otherwise, I'll see you all tomorrow. Back on schedule. Yep, thanks, you too. Marissa or Jake or Tommy, did you guys have any questions? Oh, whom did I go for in the Super Bowl? I didn't actually watch the Super Bowl this year. I don't know. I used to kind of be like more into football. I used to do like the whole fantasy thing when I was, well, man, that was a really long time ago when I was in high school. But like, I don't know. I just haven't been super into it lately, so I didn't really watch. I don't know. I guess I used to be a Colts fan since I'm from Indiana, so maybe I just would have been like against Tom Brady. Who knows? Who did you go for? Yeah, didn't really care. Yeah, then again, I have some family in Kansas, so I don't know. Maybe they were hype on it. But yeah, in any case, it sounds like it wasn't a very exciting game, so.
Good morning.
Yep, you too. See you later, Jake.